kale salad. Look at that kale.
This project's brought to you by Kale Salad.
What up? My name is Mitch Rayleigh.
What's up? My name's Jared Miller.
Howdy, y'all. My name's Austin Pham. So basically, we had 5 main goals for this project, which included, but not limited to, setting appropriate linkage measurements, verifying Grashof requirements, determining the rotation of motion of the rocker arm, determining velocity and input speed relations, and applying verified design elements to SolidWorks model for construction. Our mechanism was analyzed as a crank rocker with a single degree of freedom. This was given by the definition of a crank rocker. Our crank was the motor-driven source of mechanical power with counterweight to offset the low rocker buoy. The rocker was a lever arm used to drive this part and remove and make this guy move, you know? That guy, this guy. To ensure that derived measurements from our scaled model were appropriate, the mechanism was checked against Grashof requirements. Using the derived values and linkage, the following calculations were made. It was verified that the measurements of this mechanism passed the Grashof vibe check.
I worked on the MATLAB portion of the analysis for this dual rocker linkage, which you can see right here. You may notice 2 of the links are missing. These 2 links were needed for the analysis. The main portion of the analysis only was a 4-bar linkage. The other 2 links were just extensions and just add extra restrictions and just change the directions output. Wow, look at that rocker spin. What was that? Oh, that must be the velocity analysis. You can see from this velocity graph, while the input of the rocker stays constant, the output changes speed. Whoa! That's another graph. That must be the acceleration analysis. You can see over time, while again the velocity of the input stays the same, the acceleration of the output changes as well. And here's the code for that MATLAB right here. Wow, that must be the power of learning.
Good evening, Twitter. During this project, we used many concepts that we learned in class. Vector analysis was performed on a 3-bar and 4-bar linkage system, and the classification of the 4-bar was determined to be a Grashof crank rocker. It was a crank rocker because the intermediate member was fixed. The short member of the crank of the system was confirmed through the Grashof criteria equation, and the entire mechanism was operated by only 1 unit of input because of it having 1 degree of freedom. The position of any of the points or angles in the mechanism was able to be analyzed and graphed through the MATLAB coding and plots.
Once the dual rocker assembly was fully analyzed with MATLAB, the SolidWorks model was created. Assembly was made using 6 independent parts, including the fixed base. It should be noted that the length of the blue length was altered a little bit to portray the image in a better quality, make it easier to understand. The change of length didn't matter because it's not part of the driving 4-bar linkage within the design. The links to the mechanism are also color-coded. You'll notice that the input link will be green in ours, and the output link is red. With the completed model, a motion study analysis was carried out, and this was done to confirm that it adhered to the position constraints given within our MATLAB report. And as you can see, when the input link fully rotates, that's the green one, the red link will move back and forth in a dwelling fashion, so it'll move very fast and then stall, move very fast and then stall. And so we know that everything adheres. I still see your shadows